examples of kinds of things that can get you. And the bottom line is, be a good scientist and be skeptical of everything you come across, and decide for yourself whether it's sensible or not, or if it might not be sensible. And if it might not be sensible, look into it further. So that, if you get that message, then we're pretty much done. But let me give you some examples. I will start, though, by telling you a little bit more about how the data is specified, because if you're familiar with the way that what data specifications are, the whole thing becomes easier, at least, to navigate around the archive. But the other thing is then, of course, the data aren't perfect, the metadata aren't perfect, and I'll provide some analysis tips. So the thing that makes the archive usable, really, and reasonably easy to use, is that there's a lot of standards that are in place, uniformity across the models. Before AMIP and CMIP, you used to have to go to modeling groups, and each would give you some data in some format that was completely different from another. So we've made a lot of things uniform, but not everything is uniform. So I invite you again to review the output request, which is linked there, where they have a list of we have a list of variables and the frequencies which they've been reported. Also, what periods they're reported. For example, some of the most of the monthly data you can get for the whole length of all of the runs, but for a lot of the high frequency data, it's small samples of maybe a year for the highest frequency stuff, or 10 years, or maybe 30 or 40 years for really important daily data, even though it's pretty high frequency. The file structure, if you haven't looked at the data archive, there's one variable essentially per file. We don't put in together, for example, the U and V components of the velocity. Those are in separate files. There's a well-defined file name template shown here, or an example shown here. Basically, there's the variable name, which in this case is surface air temperature, and you'll have to become familiar with those. Those are listed up here in this standard output file if you want to know what those names stand for. There's a variable table. The variables are sort of structured in groups by domain. A means atmosphere, and by frequency, monthly. So monthly atmospheric data are all in one table. There's the model name, there's the experiment name. There's this identifier of the member of if a model performs an ensemble of simulations, that's in this point. And there's some gotchas associated with that I'll get into. And then there's the time period that the file covers. You should note that each modeling group was up at liberty to decide how many time slices to put in a single file. Some did the whole period, 1850, the whole historical period, for example, 1850 to 2005. Others, broke it up by decade or maybe in 50-year chunks or whatever, just to get reasonable file sizes. Oops. The data structure, all of the data, again, it makes it easy. Have time as the first dimension or last dimension. This is going by the, so the row major ordering. So time, level, latitude, longitude is the ordering. Pressure levels are standardized, but here's another gotcha, that there are some exceptions where some modeling group will leave out a layer, especially up in the upper atmosphere or something. So you have to be careful. Don't just pull out the levels by index, take the first 10 of them or whatever. They may not be identical. Look at what the actual values are for the pressures. The horizontal grids differ, and you'll find that pretty frustrating if you're not familiar with regridding software, but there's lots of it out there. And then the metadata conventions. Basically, there's this so-called CF conventions, standing for climate forecast metadata conventions, that govern how you store metadata in NetCDF files. And you might spend a little bit of time just sort of looking at this site, which describes it. And of course, if you have questions when you're looking at the metadata, this is one of the resources you can use. This, what we do is standardize certain netcdf attributes so that files are self-describing and machine interpretable. And of course, that enables this whole mechanistic way of being able to treat the whole archive using software as opposed to human intervention. CMIP 5, though, in addition to the CF standards, imposes additional standards, including things like we require modeling groups to register their model names, and those must be recorded in each of the files. They're used in the file names also, as you saw. Experiment names are standardized. You can look at this site to find what those are. And the variable names are standardized. That's not part of CF. CF doesn't say anything about the variable names themselves. And we require that certain units be used. So all of the temperature data is in kelvins, not in Celsius, for example, even though, of course, both of those are perfectly fine ways of, for perfectly fine units for temperature. We've made that all uniform. So this should, but again, don't always rely on this. You know, if you find a model with a temperature of 12 degrees, you can bet it's not in Kelvin. And then, some of the information, okay, so I was going to tell you about this RIP number. I won't go into details, but tell you the information is available in the DRS specifications, which is one of those documents I showed. DRS stands for Data Reference Syntax. But so these when a modeling group does several realizations, this is the common ensemble. You start a model from different initial conditions from a control run, but you're forcing it in the same way, like the historical runs. So a modeling group might produce one historical run or might produce an ensemble of 6, starting with slightly different initial conditions. Those are distinguished by a different value of the R, R1, R2, R3, and so on. There's also different initialization procedures. These are the I stands for initialization. It's sort of for these decadal prediction experiments. P is for perturbed physics ensembles, but it also was used to distinguish between runs that had slightly different forcing representations. If you look at the GISS model, they had a whole lot of different ways of trading aerosols in their model. And instead of naming those all different models, those are considered to be a perturbed physics ensemble. So you'll want to be aware of that and understand what those things mean. And again, I invite you to look at some of the documentation to get more details. Besides having the resource that's being developed here, you can always go to the original data source. So I provided that there. The data is available through grid FTP, through this threads approach, or through what are called wget scripts, or even the point-and-click web interface. The point-and-click and the wget scripts are slower, but for novices, they're sometimes easier to use than the other two options, which tend to be faster. And then there are these secondary repositories, as you know. And I should have mentioned this morning that Reto did put together a secondary repository that was greatly used, but I think it's been migrated over to the IPCC data center at Max Planck. Okay, now for some warnings. There are flaws in the metadata. Don't believe everything that's in. I mean, it's all nicely formatted in these files, and it's, the rules are followed that, you have to define your model and you have to define the experiment, but mistakes are made and the wrong information is sometimes recorded. So I don't think I have Oh, well, I do have an example of this one. Forcing, one of the things that was supposed to be recorded in the global attribute is the forcing, the suite of forcings that were used to force a model, for example, in a historical run. So you're supposed to list which greenhouse gases were in your model, you know, what kinds of aerosols you treated, whether you had solar forcing or not, and so on. A lot of groups put that in there, but it's not always right. And so I think we alluded to that this morning. There is well, I can show you in a minute. There is a summary in the IPCC report that provides some information that's in some cases corrected versions of what's on the in the metadata themselves. Another really difficult issue is when you want to compare a perturbed run like the historical run to an unperturbed run like the control run, you have to account for some purposes, you have to account for drift in the control run. These control runs are not in an equilibrium. It takes, you know, tens of thousands of years for the full ocean to really equilibrate. These control runs are typically 1,000 years or so. So they're not in pure, you know, they're not in equilibrium. There is drift, and I'll show you an example of that in a minute. But what that means is, since the control run is drifting, say like this, and you are diverging in a perturbed run away from it, you want to take the difference between those two runs as you assume the drift would have occurred in your control run. So you really need to subtract that out to get the true signal coming from the control run. So that's one thing that, because the branch times are recorded in the file, this should be easy to do, but they're not always right. So one way to check that is to just make sure that there's no discontinuity between the control run where you think it's supposed to be spawning this new perturbed run and the beginning of the perturbed run. If there's any discontinuity there, that's a hint that actually it was spawned from a different point in the control run. Oh, another issue with metadata, in going from the historical period into the future, the RCP scenarios, if you have, say, 5 historical runs and you want to have a future run that spawns from each of these, you'll have 5, you know, future runs, RCP runs. And the R value, the realization number, is supposed to agree between the historical run. That is, R1 for the historical period should continue on and be R1 for the future. But there are cases where that's not the case. So again, what you want to look for is discontinuities in when you splice together the historical period to the future period. If you're going to go through that period, then you'll know whether actually, then you'll be able to pick out which historical run really was responsible for spawning each of the future runs. Well, okay, besides the metadata, there are flaws in the data itself. Again, you should check this errata page, which I showed you. Here's an example of just part of what's on that errata page. The ocean surface temperature for the CSIRO model under sea ice was set to missing. So that means that they didn't report a value there. But in fact, for some purposes, you want to compare their model to other models that had it correctly recorded as whatever the surface temperature under the ice of the ocean was. And you know, the recommendation on how to, they didn't withdraw this data. I mean, it is useful data. But you know, you can approximately fix the problem by setting to some nominal temperature you would find under sea ice. They recommend here -2 degrees. So this is the kind of thing you can find in the errata page. But I must say that the errata page is far from being complete. We invite you to provide updates. There's Kurt Covey at our group receives emails about this and then adds it to the errata page. Besides checking the errata page, examine the output before using it. Look for discontinuities in any time series that you're looking at. Look for sign and units errors. Those are pretty common. I mean, you know, they're like 1%, but that's pretty common when you're dealing with a few million files. Look for reasonable maps. So I just give one example. A colleague of mine, Jibu Li, was interested in the wind stress field, and he said, well, can I believe, is the data I'm looking at any good? So he computed the RMS difference between the model wind stress and the observed wind stress field, and he found two really large outliers. They happen to be this BNU model and the FIO model. I'm going to show you those two models and also the Access model in this slide. Access had a low error. Here's the observed field. Here's the model that agrees reasonably well with it. And then here are the two outliers. And pretty much from inspection, you can see, oh, they probably made a sign error. And in fact, if you multiply these fields by -1, then do the comparison, then the RMS error is similar to the other models. And so there's an easy fix in this case. It's not always quite so trivial, obviously. But the point is, look at things before you start analyzing. If you just went off and analyzed all the data because it was easy to get down and then automatically process, you'd have these problems, and eventually you'd have to come back and you'd probably notice it at some point. Okay, now so those are kind of just technical issues with data and metadata, and the key word is to check things, and anything that looks suspicious, look into it. But I want to talk about some other issues or gotchas that might occur and how you might avoid them. So the model drift problem I alluded to. So even though the surface conditions more or less stabilize, there's a very slight drift, usually not that noticeable compared to the signals we're looking at. But deeper down, and so the way you count in any way case is to take the perturbed run, subtract out the control run. You might do some smoothing. There's various ways of doing this in a way that doesn't introduce extra noise into the system. But so that's one step. But for things like ocean heat content especially, drift can be a pretty important issue. And to just show an example, another of my colleagues, Peter Gleckler, in a paper showed the drift in the upper panel here in the heat content of the ocean between the layer from 2,000 meters down to the bottom of the ocean. And so these are heat content. These numbers, of course, don't mean anything to most people. They don't mean anything to me. But these are the sizes of the drifts you see in the control run. The axis here is in years. So some control runs were as long as 1,000 years and further. Many of them were more like 500 years. You see that some have dramatic warming of this layer. Others have dramatic cooling, and some have very little change. They're really reasonably close to equilibrium. But the point is, then when you spawn a perturbed run, for example, a historical run from that, and you look at then changes in this same layer, the abyssal layer, and look at the trends in the heat content, after correction, you get trends that look like this. And you can see over a period of 50 years, those trends are on the order of 5 units compared to these trends. These are units of 50 and 100, but of course, under 50 years, you're just looking at about this amount. But still, you can see that these are 10, 20, perhaps 20 watts per meter squared in the extreme cases. So these 5 watts are residual. You're taking 25 minus 20 to get 5 watts. And that's the true forced change due to the perturbation in the historical run primarily of CO2 increases. So again, you have to worry about drift, and there are ways of removing it. Whenever you subtract 2 fields, then the noise level increases, right? So you get an unrealistic. If you were just to take the time series and subtract one from the other, you'll get like 1.4 times as much noise as in the original time series. So some people try to smooth the control run before subtracting out the drift so they're not introducing extra noise. Second tip, make sure you understand all of the contributions to difference in model results. I think maybe it was Jerry was talking about this. Not all differences are due to differences in model responses. Not all differences are due to differences in model forcing. Not all differences are due to unforced variability. But all of these contribute, and here's an article that schematically sort of shows this. It was more or less quantitatively based on CMIP3 results, but take it somewhat as a cartoon, a schematic of how initially when you're doing a projection, unforced variability is a big deal, accounting for a large fraction of the difference in model responses. As time goes on, well, and the other big difference is in the model response itself. This is this is a few years after initialization occurs. So presumably these, if they were initialized perfectly, this orange thing would dip down to 0 at the very beginning. But very quickly it rises and model responses are different. And then as you go into the future, the different scenarios which lead to different concentrations become dominant. So when you're taking, the first thing is just to be aware of all of these sources of differences in model results. The second thing is don't attribute apparent differences necessarily. I mean, not all apparent differences are statistically significant in the face of climate noise. So for example, these are several realizations by MPI's model, all forced in exactly the same way, but initialized from a different point in the control run. You see they all have a slight rise in what is this, temperature over this 30-year period, but they also, because of internal variability, have a lot of variation on that. And if you asked, if you took one realization from this model, and you ask, well, does this model give you a statistically different signal from this? If you take one realization, you'll certainly get different slopes for a best fit curve or line to these, but the noise in the system would clearly tell you that they're probably not statistically significant. I mean, I'm just eyeballing, I can't. So, but the point is, when you find a difference, it could be due to noise, and this becomes worse and worse as you go to smaller and smaller scales and shorter time scales. So make sure that you don't think, well, maybe Jean-Francois showed us an example of that. Okay, not all the models included the same set of forcings. This is a table, you can't read this, but this is a table from the IPCC Assessment Report 5 showing greenhouse gases, which greenhouse gases were included in each of these models. And the table goes on for another page, so this is just a subset of the models. Y means yes, they had that greenhouse gas. You'll see some NA means no, basically. And E, for example, in the case of the aerosols, and E means that there were emissions that were specified, and then the model produced the concentrations as opposed to the concentrations being prescribed. And there's millions of footnotes here. Well, not millions. There's probably dozens of footnotes trying to explain some of the differences in the actual forcing that was used. So this is just to illustrate it. I think that they did a very careful job of putting this table together. You can rely on it largely, but there will be always additional questions you have. And again, if something really depends on knowing exactly how the forcing was done, you're probably going to have to contact the modeling groups. Now, that I wanted to also just hint at, well, I guess this summarizes what I just said, that you can have forcing differences leading to, for example, the difference between yellow and blue and purple. You can have models that are forced similarly, for example, in this case, having a spread of results. And part of that spread, although probably a pretty small part, is the unforced variability, which probably to some extent dominates part of this historical period at least. So those are the contributors. Oh, and this is just an example again about how forcing in the historical period may exhibit a discontinuity when you move into the future runs. This is from Ben Sanders' work showing stratospheric temperature response, and this is due to a discontinuity in the volcanic aerosol that was prescribed in this model. And it basically went back from a relatively pristine state of volcanic aerosol to some larger background aerosol state when they went into the future. So this affects the stratospheric temperature. You don't see it much in anything else where the noise tends to dominate. Oh yeah, and then this has to do with model uncertainty. People tend to use the model spread as a measure of model uncertainty, or of uncertainty. Now, you can say that under very kind of, in a limited way that you can actually justify saying that, but it of course doesn't include the possibility of a common bias across models, and that's sort of something we just don't know. If there is a common bias, then clearly, and you think the likelihood of there being a common bias is high enough, that should increase your estimate of what the uncertainty is in the results from the multi-model ensemble. And we need to really always keep that in mind. It's not only the models themselves, but the uncertainty in how the models were forced. There could be a bias in that, and we've seen actually in the CMIP5 models during the hiatus period that the treatment of background volcanic aerosols is not very, probably not very accurate, and maybe partially, Ben Sander may talk about this, partially responsible for the fact that we haven't had as much warming as the models are expecting. They were just forced, not right. It's not the whole explanation, but it may be partial. Okay, so again, the bottom line there really is that the uncertainty isn't really, that the model range isn't a justifiable, rigorous way of saying what the uncertainty is. And one kind of thing that gives you pause in this is that there are these perturbed physics ensembles. I think this one came from the Met Office, where they take a single model formulation, but they perturb some of the parameters. And so they get a whole ensemble of different models, really. But they looked at sea level rise pattern from their model, and this gives you a measure of the variation in that pattern across the whole model. And then they look at the variation you get from the CMIP3 ensemble in that same measure. And the variation is much larger. And the point is, if models all look enough alike, then they're probably not really sampling the uncertainty of the parameter space or the, finding all of the structural errors that we really need to be aware of. So again, don't necessarily use the range of model results as some rigorous measure of uncertainty. The last point is, in the decadal prediction runs, make sure you understand and learn about bias adjustments that are done in those. And Jerry didn't really talk about this, but just as, well, it's not just as, but when you initialize a model from observations, it will have some very fast responses initially where it tries to relax to the climatology it really is comfortable with. In other words, another way of saying this is in a control run, the model is all adjusted and kind of in a quasi-equilibrium. If you force it away from that by initializing it with observations, which, if the model doesn't perfectly agree with observations, you force it away from that, it's going to try to return, And a lot of that return takes place relatively quickly. And in every one of the initialized model runs, you'll see an initial transient, and then you'll see things evolve after that. And that transient is artificial. It's just because the model is trying to go to its climatology. And that transient has to be removed if you want to actually get the trajectory of what this model is predicting for climate. So that's a bias correction that's done. And there are some bias corrected data available in the archive, but it's only for surface temperature and precipitation, I think. And not all the models did that. So if you look at the raw data for the decadal predictions, you have to do that bias correction yourself. It's non-trivial. There are lots of different approaches, and I would stay away from it unless you want to invest time in really learning how to do it right. So I'll leave you with this summary, but I think I'll quit there because I'm over time. Thanks.